So in this lesson, we're going to talk about absolute dating. Now we talked before about relative dating, which is where we were comparing the ages of rocks from one to another. Now in this lesson, we're going to be looking at absolute dating, which is looking at how to find radioactive isotopes and how they're used to find the ages of rock layers or fossils. We're going to identify which radioactive isotope we would use for different materials, because different isotopes are better for different things. And then we're going to calculate the number of half-lives a sample has undergone. So we're defining absolute dating, radioactive decay, and half-life. Those will be our big vocab. We're explaining how radioactive isotopes decay, so what is it that they're doing, and how that's used to find the absolute age of a rock layer. Then we're going to determine the best isotope for a certain layer, knowing what kind of rock it is, knowing how old it might be. Then we're going to calculate the number of half-lives in a sample if we're given the age of the sample, or we're going to calculate the age of a sample if we're told the percent or fraction remaining of the sample. So just a little bit of background information before we start. An element is a pure substance made from a single type of atom. It cannot be broken down into simpler substances. So an element, an example, would be carbon, oxygen, nitrogen, hydrogen. Those are elements. If you think about the periodic table of elements, that's what you think about. Now an atom is basically a single piece of an element. It is the smallest particle of matter that retains the properties of that element. So I could have many atoms of a certain element, or I could have one atom of a certain element. The number of protons in an atom determines what the element is. So if we look at this model of our atom here, right? So in the middle, I have orange and red. My orange are my neutrons, my red are my protons, and then on the outside I have electrons. So the protons, those positively charged subatomic particles, are what determines what the element actually is. Then we have things called isotopes. So if we're looking at these here, right, I have carbon 12, carbon 13, and carbon 14. So notice the number at the end is different, right? That's because if you add up the number of protons and neutrons, you get this number. So this number is called the atomic mass of the atom. Carbon 12, which is just regular old carbon on the periodic table, has 6 protons and 6 neutrons. Notice that all of these have the same number of protons, because that number determines the element. But they have different numbers of neutrons. So an isotope has the same number of protons, but a different number of neutrons. And since neutrons don't carry a charge, they don't affect whether it is positive or negative. It's just adding a little bit of atomic mass. And isotopes are naturally existing, but tend to be less abundant. So if you look at the percentages here, 98.9% of carbon found on the Earth's surface is carbon 12, carbon 13 is 1.1%, and then less than 1% of carbon is carbon 14. Now if you look at radioactive isotopes, these are isotopes that are unstable. So you can have regular isotopes, you just have an isotope, or you can have one that's radioactive. So these are unstable and they break down into other isotopes through a process called radioactive decay. So these are kind of our big ideas here. These are radioactive isotopes. The process in which they break down is decay. So what happens is you have a parent atom, so you have an unstable parent atom. Because it's unstable, it can't stay the way that it is. It gives off energy and particles and changes into a new kind of atom known as the daughter atom. So this unstable atom, it can't stay the way that it is, releases some energy, releases some particles, and then what's left is a stable daughter atom or daughter product. Now the half-life is a measurement of time. Okay, so these things happen in a way that is measurable. So half-life is the time it takes for half of the radioactive atom to decay. So say you had 100 to start. The half-life would be the amount of time it would take for 50 to decay. The rate of decay for this is constant for each radioactive element, and this can be measured experimentally by scientists. So when we look at radioactive isotopes in this class, we're really just focusing on these 4. So this is the radioactive isotope, The disintegration column is what it's changing into. So what you'll notice is there's a number. So this is an element, carbon 14, and then you have nitrogen 14. So this is what it starts as, and then this is the product, nitrogen 14. And then you have the half-life, which is the amount of time it takes for half of the atoms to decay. You look at this diagram down here, I have all parent isotopes at 0 half-lives, and then at 1 half-life, half of them have turned into daughter products. 2 half-lives, another half of what was remaining here has turned into daughter products, and that process will continue until there's no parent isotopes remaining. So when we think about how we use this process, when igneous or molten rock cools, so igneous rocks are made of magma or lava, depending on how they form, radioactive atoms are trapped inside. So as these become older, those radioactive atoms begin to decay into stable atoms, because remember, radioactive atoms cannot stay the way they are. They're unstable and they have to change. So what we do when we use radioactive decay to find the age of something is we compare the number of parent atoms there are in a sample to the number of daughter atoms. And by doing that, we're able to determine how many half-lives have gone by. So for example, if there's 50% of parent and 50% of daughter, then I know it's 1 half-life. If there is 12.5% of parent remaining, then it's 3 half-lives. 25% is 2. I should have done that in order. So it's 50%, 1 half-life, 25% is 2 half-lives, and then 12.5 is 3, and so on and so forth until you run out. So the more daughter atoms you find in a rock, the older it is, because the more time has gone by for those unstable atoms to change into stable atoms. This is just an example that we can go through in order to sort of understand how this works. So if you imagine you have 100 grams of a substance that has a half-life of 1 hour. At time 0, okay, this is our start time, you have 100 grams of the parent, the unstable, 0 grams of the daughter because nothing's happened yet, and this would be 0 half-lives. So after 1 hour, if the half-life is 1 hour, right? So after 1 hour, that would be 1 half-life. The new mass of the parent is going to be 50 because it's half of the original. And now if 50 of it is remaining, that means 50 of it turned into daughter product. And again, it's 1 half-life. Now after 2 hours, it's 2 half-lives. So it's half of this current amount of parent. So now we're going to have 25 grams. And the daughter product is now going to be 75 grams because I already had 50. Another 25 turned into daughter product, so you have 75 grams. And you have to remember, if you start with 100, you always have to keep to 100. It can't ever be less than that. So this would be 2 half-lives. So again, I'm going to take this number, I'm going to divide it by 2 because that's half, 12.5 grams. I'm going to add the 12.5 to the 75 because I already had 75. Now I have 87.5 and it's 3 half-lives. And then we would do it one more time for 4 half-lives. So this is just sort of the way you can think about it. Every time you go through the parent mass, every half-life divides by 2. When we're looking to find the absolute age of something, we want to know, first of all, how much parent's remaining. So if I have 50% of parent remaining, then it's 1 half-life because it's half, right? So whenever we do these things, if you're given a percentage, you need to figure out how many half-lives have gone by. That's always going to be the first thing you have to do. Now, what if there is 12.5% remaining? Okay, so 1 half-life is 50. Okay, 2 half-lives is 25. 3 half-lives is 12.5, because remember, this keeps getting cut in half. So we'll talk a little bit about the different methods of radiometric dating now. The type of isotope that you're going to use or you're going to test in something depends on the material you're looking at. So in geology and for earth science, we're using, generally speaking, igneous rocks. And the half-life of the isotope is also important. You can't be too short or too long compared to the age of a sample. If you're looking for something that's very, very old, like 4 billion years old, but the half-life of your sample is very short, you won't be able to find out how old it is because there won't be anything left and you won't know how long ago it ran out of parent atoms to decay. carbon-14 tends to be the one people are most familiar with. So carbon-14 dating is looking at carbon-14, which is, again, that radioactive isotope. It's used to date wood, bones, shells, and other organic remains. So when we say organic, what we mean is used to be or is living. And it's only good for about 45,000 years. So this is not really useful for geology. This is often used in archaeology because we're looking at past human civilizations and the materials left by those civilizations. The half-life of carbon-14 is only 5,700 years old. So after 45,000 years, any carbon-14 that was in existence in something is no longer there. There's nothing left to measure. So it's only really good for about 45 to 50,000 years. Potassium-40 and uranium-238 we're going to use in geology more often. So potassium-40 has a half-life of 1.3 billion years. Is used to age rocks older than 100,000 years. Uranium-238 has a much longer half-life, so this is only going to be useful for rocks that are much older. So depending on what you're looking at, what you already sort of may know about the ages of the rocks based off of relative dating, you would choose your isotope based off of that. So when we find out how old the Earth is, we use radioactive dating to find the oldest rocks, which are about 4.3, maybe 4.6 billion years old. And then oldest fossil hasn't been found, is only about 3.5 billion years old. But a lot of the beginning of Earth's history was formation of the atmosphere. There had to be conditions on Earth's surface for it to have life. So we spent about 1 billion years just sort of creating those conditions. Okay, so again, we want to look at how they're used to find the ages of rock layers, identifying the isotopes that are best for finding ages, and calculating half-lives. You're either going to calculate the number of half-lives a sample has undergone or calculating the percent remaining if you are given